Okay, so here we talk about Gauss law applying for planar symmetric,平面对称. So for this case, we have a non-conducting sheet. It is thin, infinite, and non-conducting. So actually, for non-conducting means there may be charge distributed inside a non-conductor object. However, here we assume that it is thin, which means infinite thin, so it doesn't really matter it is conducting or non-conducting. It looks quite the same. Actually, we can really assume that the charge is non-uniform, but in this case, it's still uniform. But so if you ask, what is the difference if I just make it conducting, then there will be no difference for this case. So here we applying the Gauss law for this one. We have a thin, infinite, non-conducting sheet, and the surface charge density is sigma. So it will generate the E field on the left side and on the right side. So the Gaussian surface we define here is also a cylinder, and as we know, the E field is perpendicular to the plane, so there will be no net force contributed by the side. And so this integration only have EA contribute by the right part and the left part for this one. So we have EA plus EA for this side and that side. A is the area of a circle, and actually it's a cylinder, so the charge enclosed by this cylinder will be this part, which will be the sigma times the A. Sigma times the A will be the charge enclosed. So here we will just cancel the A and divide 2 epsilon 0 on both sides. So we have the E field generated by the infinite charge plane is sigma over 2 epsilon 0, which is actually the same as this one. So next, suppose we have two conducting plate. So for this part, assume that you only see this one and you only see this one. They do not have interaction yet. Suppose you put this infinite far away, and then you consider this one. So the charge will be distributed on the left side and on the right side. So sigma 1 is the surface charge density also, and the E field generated by this plane would be E plus. There is assume that it is positive charge distributed on this plane, so it generates E plus, which is sigma 1 over 2 epsilon 0 on this side and also on this side. But on the left side, it points to the left side. On the right side, the E field points to the right side. And we assume that this plane has a negative charge. The charge density is actually the same as this one, but they have opposite sign. So the E field generated by this conducting plate would be E minus. The magnitude is actually the same, sigma 1 over 2 epsilon 0. but the E field point to the right side on the left part, and the E field point to the left side on the right part. So the magnitude is the same, but the magnitude but the direction is opposite. The direction opposite. So suppose we put these two plates close. Put these two plates close. So all the charge, the positive charge will go to this side. The negative charge will go to the left side. Actually, the positive charge will attract the negative charge. They will attract each other, so all the charge will distribute at the inner surface. So in this case, all the E field will be concentrated to the right side for the positive component, and E will be 0 at this side. For the negative plate, all the E field will be concentrated at this part. So the magnitude will be double, and at this part the E field will be 0. And now the surface charge density will be double because all the charge go to one side. So the overall charge generated by this structure is E plus E minus. So this term plus this term will be 2 sigma 1 over epsilon 0. So cancel these two for here. And we define the new surface charge density sigma to be so we do not call it 2 sigma 1 anymore. We call it sigma, which means that sigma equals to 2 sigma 1, which is the new charge density. So it turns out E will be sigma over epsilon 0. So this structure will appear in chapter 25, which is actually a capacitor. Then wrong. So up to now, any questions? So we move on. So the portion of two large parallel non-contact sheets, which with a fixed uniform charge on one side, the magnitude of the surface charge density sigma plus is 6.8 μ coulomb per meter square. However, the sigma minus is smaller, and it is negative. So find the electric field to the left of the sheet and between the sheet and to the right of the sheet. So here we can calculate it like this. So actually, we can assume that because not all the charge will be distributed at the inner surface because they have different amount of charge. So we can consider like this: E plus. E plus will be sigma plus over 2 epsilon 0, which means that it will generate E field on both sides, like show it here. On both sides, we can just ignore this plate first. So it will generate a E field by the positive plate. And for the L part, it will point to the left side. At the B and R part, it will point to the right side. So the magnitude will be 6.8 times 10 to minus 6 over 2 times 8.85 times 10 to minus 12. So it will be 3.84 times 10 to 5 Newton per Coulomb. And for the negative plate, likewise, we can calculate like this. However, for the negative plate, for the L part and B part, you point to the right, and for the R part, you point to the left because it is negative. So the E field direction should be opposite. So we can actually write it like this. Substitute the value 4.3 times 10 to minus 6 over 2 times 8.85 times 10 to minus 12, which the answer will be 2.43 times 10 to 5 Newton per Coulomb. So the left part, we can just add them together. We can just actually subtract them because EL will be this one, E plus, point to the left side as shown in this graph, E plus, and E minus should be point to the right side. So actually EL will be E plus minus E minus. So it will be 1.4 times 10 to 5 Newton per Coulomb, which points to the left side. So this is the part A. For part B, between EB would be actually E plus point to the right, E minus point to the right, so it will be E plus E minus, which has the answer 6.27 times 10 to 5 Newton per Coulomb. Point to the right. And for the right part, it will be actually the same. Actually, the magnitude will be the same as the left part. Actually, the same as left part because we will have E plus minus E minus, but it will point to the right side. So actually, it will be nothing but 1.41 times 10 to 5 Newton per Coulomb point to the right. Okay. Any questions? No. Okay. So next we talk about applying Gauss law for the spherical symmetric. So in chapter 21, we talk about the shell theorem. There are two statements in the. There were actually two statements for the shell theorem. At that time, I told you that it's hard to really explain why it would be like this, but now I can tell you the reason by using the Gauss law. So at that time, it tells you that a shell of a uniform charge attracts repels a charged particle that is outside the shell if all the shell charge were concentrated at the center of the shell, as if all the charge is concentrated at the center of the shell. So for this case, the charge Q is actually distributed here. You can assume there is a shell here, so all the charge is distributed here, and we assume a Gaussian surface S2, which has a larger radius than capital R, which is a small r, and actually that's why I mentioned uniform is important, because as long as this is uniform, we have a spherical symmetric. In this case, we are applying the Gauss law so that we can have something like the so we have a Gauss law epsilon 0, this integration dA equals to Q enclosed. So Q enclosed is actually Q, and the epsilon 0 is this one, and for the spherical, the surface area is 4 pi r squared. So we have something like this, and actually it's just like all the charges distribute here. As long as it is distribute uniformly on a shell at the outside, you will feel that it's actually the same to be something like all the charges distributed by the center. So this is the first statement of the shell theorem. And the second statement is that if the charged particle is okay inside a shell of the charged particle is located inside a shell theorem. No. So suppose a charge is located still at this shell, and there is no electrostatic force on the particle from the self-in. Suppose the charge is inside the shell. Suppose the charge is inside the shell, there will be no electrostatic force, because here we applying applying Gauss law to the surface S1, which has a smaller radius than the shell. So in this case, the charge enclosed by S1 should be 0, which means that E should be 0 inside the shell. And there is no E field, so there will be no electrostatic force. So this is the explanation for the shell theory using Gauss law. So next, we can still applying the Gauss law for the spherical symmetric. So here, we assume that the charge is distributed on a non-conductor sphere, which has a uniform distribution, uniform volume charge density. We assume a uniform volume charge density inside a sphere. So actually, in this case, the E field inside this sphere will not be zero. Will not be zero. For a conductor, all the charge will distribute on the surface. Then there will no E field inside there will be no E field inside the conductor. But here there will be E field, so we try to calculate it using the Gauss law. Suppose the charge density is rho, the volume charge density. So Q is the total charge, distributed on the sphere, and actually the volume of a sphere is 4/3 pi r squared. 4/3 pi r squared. So you should have learned it in high school, and also you should know how to derive it using the single variable calculus. Actually, the integration, you can use the integration to derive it. So suppose we have a Gaussian surface which has a smaller or equal radius than capital R. Capital R is the radius of the sphere, but here we define the Gaussian surface with a radius small r, which is smaller or equal to smaller or equal to capital R. So the rho should be like this: the total charge divided by the total volume, because it is uniform. And so for the inner part, which is the Q enclosed, but the volume is only up to small r cube, which is because it is still a sphere, but a smaller sphere. So we subtract the radius of the Gaussian surface here, and it is uniform. So these two should be the same. So we can have Q enclosed equals to Q multiply R square over capital R, R cube over capital R cube, and 4/3 pi can be cancelled. So we have the Q enclosed like this, which is related to the distance from the center. So applying the Gauss law on the left side, we still have epsilon, and E is constant. So we just multiply E by the surface area, which is the net flux. So it is 4 pi r square, and Q enclosed is this one. So we substitute it here. So r square and here r square can be cancelled. So only r is remain, and r cube. So we have k q r over r capital R cube over capital R cube. So the E field inside the non-conducting sphere, which has a uniform charge distribution, is like this, which is proportional to the distance from the center. Any questions? So it's something like if this is a single charge, the E field is inverse proportional to the square of the distance. However, in this case, it is a sphere, and the charge distribution is uniform. So the charge is increased to the third power of the distance. So overall, the E field generated by this one inside the sphere is proportional to the distance, proportional to r. For r smaller than capital R. And for the outside sphere, it is trivial because when we apply the Gauss law, all the charge will be enclosed by the Gaussian surface. So Q enclosed is Q, and for the left side, it is still this one, but Q enclosed is Q for R larger than capital R. So for the outside part, E is KQ R squared, which just like all the charges distributed at the center. So in this case, this graph shows the E field versus the distance from the center. So inside the sphere, it is it increases proportionally and decaying to the second power to the distance outside the sphere. Any questions? So we have an additional problem at the end of this chapter. So actually, this is the problem of in the textbook. Last year is one of the selected problem, but I choose all the selected problem again, so it is not in the selected problem anymore. So this will be a little bit challenging. The volume charge density of a solid non-conducting sphere of a radius r, capital R, varies. The charge density varies. Charge density varies with respect to R, which means that the rho is not a constant anymore. It is this one multiplied by small r, and this one is a constant. This one is 5.6. So so this is just like close to the center. At the center, the rho is 0, but at the surface of the sphere, it is actually 35.4 picocoulomb per meter square, meter cube. So what is the total charge of the sphere? And actually we need to calculate using the triple integration, which will be something like this: rho dV. So we integrate the rho with respect to the whole volume. And actually, it is a spherical coordinate， 球坐标，或者是叫球面坐标。Spherical coordinate. You may have learned it in a multivariable calculus class that I just show you a bit. So it will be something like this. From 0 to R, and rho is rho. Maybe I can just let this term, we call it rho s. And actually dV dv will be r square sine theta dr d theta d phi. So actually, the spherical coordinate will be something like this. Then this is the xy. Maybe this one is x, this is y, this is the z direction. So you have the projection on the xy plane, and actually the point to the center will be out. We use this one, and then this angle will be phi, and this angle will be theta. So the volume of this part will be r square sine theta times dr d theta d phi. You will learn it in calculus class, no problem. But just let you know now. So sorry, I forgot something. So actually this rho should be rho s r over capital R. Should be something like this. And you can see that this integration is easy because you can separate the variable, which means that we can actually separate So first of all, rho s is a constant. Capital R is a constant. So that we can just push it out. And next for dr, we have r cube, because we have one r, we have r square, so we have totally r cube, and we integrate from 0 to capital R and dr. And sine theta is integrate from 0 to pi. So actually we can write it as 0 to pi sine theta d theta. And the next part will be d phi. We have no phi, which means we integrate 1 d phi from 0 to 2 pi. So this integration will be easy because you can separate them one by one. If they are mixed together, then you cannot just simply separate them. So actually, we have rho s over r, and this one, the second one, will be r to the 4th power over 4. And then next, this one sine theta integration is minus cosine theta, and then you substitute pi and 0, and then you subtract them. So this one is 2. For this one, you integrate 1, so it is 5, and then you substitute 2 pi and 0 and subtract them, so it is 2 pi. So you finally find that the charge will be pi rho s r to the 3rd power, which means that 3.14 times 35.4 times 10 to minus 12 times R, what is R? 5.6 centimeter, 0.056 to the third power. So it is actually 1.95 femtocoulomb. So this is one of the reasons why I select the sample problem again, because in the last semester I do not have I do not have too much time to prepare all the selected problem again. I just absorbed it from Professor Ho. So it may be difficult for you, but actually it's not really. So for the next question, ask you what is the E field at R equals to 0? At R equals to 0. So actually this is very, very easy. The answer is 0. The answer is 0. The answer is 0. Because you can simply draw a Gaussian surface to be very, very small, and then the Q enclosed will be very close to 0 because this is actually 0 at the center, so there will be no charge at that point, and due to the symmetric property, then there should be no E field inside, or there may be E field outside, but at the very center, all the E field should be cancelled at that point. So next, what is the E field at R equals to capital R over R cubed? So for this case, we still need to calculate the Q enclosed again. So similar to question A, we need to integrate the charge enclosed by a Gaussian surface with a radius small r, or capital R over 3. So actually it's like this, and maybe we can write it as R prime because we already have a R here, so we may use R prime here. Okay, so we make it R prime, but now we do not integrate from 0 to capital R again. We only integrate from 0 to small r, or capital R over 3 in this case, because the Gaussian surface will be like this. And for the other two coordinate, which will be actually the same, so we can write like this. One we can just ignore it, so which is Rs over R, and this case R to the 4th power over 4, and this is still 2 and 2 pi. This is still 2 and 2 pi. And we can so in this case, it is actually equal to epsilon 0 E 4 pi r square using the Gauss law. In this case, E is rho s r square over 4 epsilon 0 r. So actually, so pi, this is not 2.2. So pi and pi can be cancelled. So now we don't have a pi here. R to the 4th power and R to the 2nd power. We only have R to the R square remain. And we have capital R, rho s. And 4 and 4. 4 and 4 is cancelled. So we have only this 4 left. So actually, it's something like this, and we can substitute. Rho s is 35.4 times 10 to minus 12 times R is 0.056. Or maybe I should write it as E when R equals capital R over 3. It will be more rigorous. R over 3 square over 4 times 8.85 times 10. 8.85 times 10 to minus 12 times 0.056. So it will be 6.22 times 10 to minus 3 Newton per Coulomb. Okay, so next, R is equal to R. R is equal to R. We just calculate Q equals to pi rho s R cubed. And it will be equal to epsilon 0 4 pi r squared. Or maybe I can write it. Yeah, r squared. So we assume that r is larger or equal to r. So we will get the expression like E. Forgot the E. So E will be so in this case, R is smaller than R. In this case, and for this one, when R is larger or equal to R, E will be rho s over 4 epsilon 0 R to the third, capital R to the third power over R squared. Okay. So if R equal, so this case R is larger or equal to capital R. So if R is equal to capital R, then E will be rho s over 4 epsilon 0 multiplied by R. And we substitute 35.4 times 10 to minus 12 times 0.056 over 4 times 8.85 times 10 to minus 12. So it is equal to 5.60 times 10 to minus 2 Newton per Coulomb. Okay. So finally, graph E versus small r. So it will be something like this. This is R, this is E, and this is R. So actually it is inverse proportional. E is inversely proportional to R squared. Sorry, E is proportional to R squared, and inverse proportional, still inverse proportional to R squared outside, but the yeah, inverse proportional. So you can see that it is still inverse proportional to that, but the constant is different. If it is a unit, if it is a single charge inside, so you need the integration to really calculate. Okay, something like this. So and at this point it is 5.6 times 10 to minus 2 Newton per Coulomb.